Welcome back to Linear Systems and Signals. So now we're going to dig into the type of systems we're going to be looking at for the rest of this class, which are linear time-invariant systems, or LTI systems. So just the purpose of this presentation is just to give you a little bit of introduction to LTI systems and the kind of way in which we're going to be thinking about them. So obviously you want to know what LTI systems are, so we want to know how linearity and time invariance go together. So it turns out that the combination of linearity and time invariance is really useful. They kind of fit well together, and we'll see that sort of in a graphical way. And that will sort of show us that we can do operations, we can describe the operation of LTI systems in a relatively simple way. So what do these two quantities or two properties mean? Linearity means you can interchange linear combinations in applying the system. So instead of applying h to x1 and h to x2 and then adding them up, you can just take x1 plus x2 and apply h there. Why is that important? Well, you would have to build a circuit, say, for example, to implement h, and this means, linearity means that you could get away with building one circuit as opposed to two circuits, two copies of the identical circuit. So what about time invariance? Now, time invariance means you can swap a delay and the application of the system. So you can either delay something by 5 seconds and then apply the system, or you can apply the system and then wait for 5 seconds, and then that's delay the output by 5 seconds, and you'll get the same thing. So we're going to be studying systems which have both of these properties. They're both linear and time invariant. And we're going to use the term filter to describe these systems because a lot of the systems that we're going to be looking at are going to be filters of some type. They're going to take a signal and filter out some part that we don't want, or use a filter to keep the part that we do want. So that's sort of the metaphor you want to have in your mind, and filter is the name that they get called kind of everywhere in engineering. So let's look at, in pictures, what does linearity mean? Right? So linearity means that you can take x1 and x2, you could apply some gains to them and add them up, so then you get a1x1, plus a2x2, that appears right here, and then you apply h to that, so here you have your h, and then you get out y, right? And the question is, can I get this y a different way? And the answer is yes. You can actually take this h, and if you can think about it as like pushing it back through the system. So you push it back through the sum and then back past the gains, and it turns out you can just apply h to x1, h to x2, multiply them by some gains, and then add them up, and you'll get the same y of n. Right, so like I said before, this second version requires two implementations of the system h, and this top one requires only one. So this is what linearity can buy you. What about time invariance? Well, time invariance is a property that says that if xn is mapped to yn by our system h, right, then if I take x and delay it by k, n minus k, it's the same as taking this original yn over here and delaying it also by k. Right, so what does that mean in pictures? Well, this first part here means that xn goes to yn when you apply h, and the other one says that the following two pictures are equivalent. I can take xn, delay it to get x of n minus k, that's x delayed by k, and apply h, and I'll get y of n minus k. Or I can take x of n, apply h to get y of n, and then just delay by k, and I'll get the same y of n minus k. These two signals are exactly equal to each other. And so that's what time invariance says. So in order to apply these two properties, the key ingredient we're going to need is this way of representing dt signals as a sum of impulse functions. So if I have a dt signal, it goes along x minus 2, x minus 1, x 0, so these are the samples of the discrete time signal. I can write it equivalently as x minus 2 times delta of n plus 2, so this is a delta at n equals minus 2, and this is a delta at n equals minus 1, and so on. Here's a delta at n equals 1, and so on. So more compactly, I can write it in this following form. I can say that my signal x of n is just the values of the signal at time k times an impulse function at time k. So nothing really fancy is going on here. I'm just using this algebra to write down my signal in a slightly different way. But what I can do is I can draw a picture to explain what's going on here, right? And so what I can say is that I can think of the delta, these impulse functions, as signals themselves. So there's an impulse function at time 1. It gets multiplied by x1, and then I add it to xn. Similarly, at time 2, multiply by x2 and add it to time n, right? So this xn here is equal to the sum of x of k, delta of n minus k, for k equals minus infinity to infinity. And those are these dots going up and down. Okay, so what is the point of this? I mean, okay, looks fine as a picture, whatever. Well, the key thing is all of those delta functions, all the delta functions, deltas, are related. And how are they related? They're all delayed versions of this original delta function, just a delta function at 0. So I can delay it by 1, and I'll get delta of n minus 1. I'll delay it by 2, and I get delta of n minus 2. And similarly, at time k, I get delta of n minus k. So I've done nothing but replace those from the previous slide, those deltas, with a different way of writing it, which is to say take the same delta function and delay independent copies of it by 1, 2, 3, 4, say, all the way up to k. So I get to do this, and now what we can see is like, oh, we can think of x of n as the output of a system that I applied delta of n to. So I applied delta of n, and then I get this x of n out. So how are we going to understand this, and what it will tell us about how LTI systems work? Well, the question we need to answer then, and that's what we're going to answer in the next few presentations, is what happens when I put this h sitting at the output xn to get y of n. Can I take h and somehow manipulate it through this block diagram to get a different explanation of what's going on when I use an LTI system? So h is LTI. So if it's LTI, what can we do? We can take h and we can push it back through, and then we can apply the time invariance property to swap the delay and the h, and we'll see, just using those same pictures that we saw earlier in this presentation, to basically prove a very fundamental theorem, which is that the output of an LTI system is what's called the convolution of the input with something called the impulse response, which is the output of h when you apply a unit impulse. So more on that in the coming slides, but this is just a little preview to get us warmed up.